Welcome. In today's video, we'll introduce the concept of finding the arc length of a curve. We'll be using integration to find those arc lengths. And there are a few formulas that usually are typically used when we try to find the arc length of a curve. And we'll introduce each one of them. They basically are more or less the same formula, but for specific cases. So the first formula is given to us when we deal with a curve of the form y is equal to f of x, right? Meaning y is a function of f of x, right? So in that case, for a curve of that form, we need to also have the fact that f prime of x, right, which is the derivative of the function, is continuous, right? So that function has to be continuous on some interval a to b, right? So the derivative of that function has to be continuous on that interval. And when this condition is fulfilled, the length of the curve between A and B, right, is given to us by the formula there. So the length L is equal to the interval from A to B of the square root of 1 plus the square root of 1 plus dx dy, right, squared, all under the square root dy, right? So that's what the formula tells us, right? So for this specific case, we are trying to find for this formula here, we're trying to find the length of that curve as y is varying. So I think that is where the first case is defined as, right? So here we're trying to find the length of that curve as y is changing, right? The second case, which is the one below here, is just a case where we are changing now the function in terms of x. Okay, so in fact, sorry, I think I made a mistake here. For this first case here, this should be the other way around. So that would be x defined in terms of y, because y is the function that is changing, right? And therefore the function, the condition that we need to be defined is that the derivative of that function is continuous on that interval, right? Meaning a and b are just changes in terms of y, right? And then the second case would be the opposite now. It would be what we had initially for the first case, which is y is a function of f of x, meaning that f prime of x will have to be continuous, right? Will have to be continuous on an arbitrary interval c to d, right? So, well, the interval is not arbitrary, it's defined, but it's from c to d. So it's a specific section of the curve, right? That is defined on the x-axis, right? Between C and D, right? So that's it for the second case. Now for the third case, that's where we have now parametric functions. So in this case, as you can see, the formula is given to us as L is equal to the integral from C to D. Again, these C and D are just letters that we assign to the specific boundaries for the section of the curve that we're looking at. So don't pay too much attention to those, but pay attention to the actual formula here under the square root sign. So this here tells us that we have to derive, right? To find the length of this curve, we take the integral in the defined section, right? In the defined section from C to D of the square root of the square of the derivative of y in terms of t, right, squared, plus the square of the derivative of x in terms of t, right, all under the square root sign dt. So, and what that tells us is that we have the case. So for this third case here, what we are having here is that we have y is a function of t, and x is also a function of t, right? So t can be time, it can be any other arbitrary variable, but it's not x and y. So x and y are functions of a third variable that can be represented in general as t. And I think in most cases that we'll be dealing with, t will be some sort of time or angle. Sorry about that. Yes. So that is it for the three formulas. Now we'll look at a few examples to sort of illustrate what we mean here. So let's look at this. The first example. The first example is asking us to find the arc length, right? So we have to find the arc length of the curve over the interval that is given to us. So for the first case here, we have an interval in terms of y, meaning we have to use the formula that tells us L is equal to the interval from A to B of the square root of 1 plus dx over dy, and here there's a square. So that's the formula that we have to use for this case. Now, we have to first find what is dx over dy. So the function is given to us as x is equal to 1/3, 1/3, of multiplied by y squared plus 2 to the exponent of 3/2, right? So that would mean that we have to find the derivatives in terms of y of 1/3 times y squared plus 2 all to the 3/2. Now, this takes us back to our derivatives, and this should be equal to the 1/3 is a constant, so we leave it out. The derivative of y squared plus 2 to the exponent of 3/2 will just be, we'll have to take down the exponent first, which is 3/2, multiplied by the same function, y squared plus 2. Now to the exponent of 3/2 minus 1, right? Multiplied by the derivative of y squared plus 2, which is just 2y plus 0, so 2y. Here I use the chain rule, so you can go back to the exercises that we did using the chain rule to sort of understand what we did here there. So now that we've done that, we can simplify this expression further. We have the 3 here that can cancel, and the 2 here that will cancel with the other 2 there. So now we are left with the y, right, multiplied by y squared plus 2 to the exponent of 3 over 2 minus 1, which is just 1 over 2, meaning the square root, right? So basically what we have here is y multiplied by the square root of y squared plus 2, right? Now we have to square that. So we have to find dx over dy squared. Let's go down. Dx over dy squared is equal to, therefore, y multiplied by the square root of y squared plus 2 all squared. And that just gives us y squared multiplied by y squared plus 2. Right? So we have that. Now we'll take it back into the formula, which is just L is equal to the integral. We know that y is changing from 0 to 1. So the boundaries are the integral from 0 to 1 of the square root of 1 plus the square here, which is just y squared multiplied by y squared plus 2 squared. Oh no, we've already squared it. So no need to do it a second time. dy. And this is equal to, let's try to see if we can simplify this any further. Right. So we have the integral from 0 to 1 of the square root of 1 plus y squared, y to the 4, right? So we'll multiply the y squared into the parenthesis. So we have y to the 4 plus 2y and dy. And as you can see, this is just equal to the integral from 0 to 1 of the square root of y squared plus 1 squared, right? So that is a quadratic equation. And since we have that, right, dy there, since we have that, this is just equal to 0, the integral from 0 to 1 of y squared plus 1 dy, which is just equal to y cubed over 3 plus y evaluated between 0 and 1, which gives us 1 over 3 plus 1 minus 0, which is just equal to 4 over 3. So that should be our final answer. Right? Now, let's move on to the second example, which is the curve that we're given is now y is equal to x to the 2 over 3, right? And we are evaluating the length of that curve between x is equal to 1 and x is equal to 8. So immediately, as soon as we see that, we know that we have to deal with the formula that tells us L is equal to the integral from c to d of the square root of 1 plus dy over dx squared all under this square root sign. Right. So now that we have that, the first thing that we need to do is find what is dy over dx. We know that that's just the derivative of x to the 2 over 3, which is equal to 2 over 3 multiplied by x to the 2 over 3 minus 1, right? And this is just equal to 2 over 3 multiplied by x to the negative 1 over 3, right? So we have that. And then we have to square it to find dy over dx squared, which is equal to 2 over 3 times x to the negative third squared, which is equal to 4 over 3 times x to the negative 2 over 3. Right, so we have that. 4 over 9, not 4 over 3, sorry. 4 over 9. And now that we have that, we'll take it back to the formula. And this will give us L is equal to the integral. The boundaries are from x is equal to 1 to x is equal to 8, if I'm not mistaken. Yes. So we have the boundaries. And that integral of 1 plus the square root of 1 plus 4 over 9 x to the negative 2 over 3 dy. All right. So now that we have that, we can try to simplify the expression to see if we can solve this integral easily. So let's first get rid of the negative exponent. So we have the integral from 1 to 8 of the square root of, and what we'll do is we'll multiply and divide by x to the 2 over 3, right, to get rid of that. And what we get is under the square root sign, right? So what we get is x to the x to the 2 over 3 plus 4 over 9 right, all divided by, right, so this is under the square root sign, so all divided by x to the 2 over 3, right, dy or dx. Yeah, my mistake, it should be dx, not dy. Dx. Right, so now that we have that, let's see if we can take it further. And we can pull out the x to the 2 over 3 in the denominator from the square root sign. So we have now L is equal to the integral from 1 to 8 of 1 over x to the 1 over 3. Because remember, as soon as the x to the 2 over 3 comes out of the square root sign, you have to divide the exponents by 2, right? So you have x to the 1 over 3 there, multiplied by x to the 2 over 3 plus 4 over 9 dx, sorry, which gives us the integral from 1 to 8 of x to the negative 1/3 multiplied by x to the 2 over 3, the square root of x to the 2 over 3 plus 4 over 9 dx, right? So we have that. And here, at this point, we can use now our different methods to solve this integral. Namely, we'll use u substitution. So we'll let u be equal to what's under the square root sign. So x to the 2 over 3 plus 4 over 9, meaning that our du over dx will be 2 over 3 x to the negative 1 over 3, meaning that dx is equal to 3 over 2 multiplied by x to the negative 1 over 3 du. And now that we have that, we can take it to the original integration, and therefore we have L is equal to the integral from 1 to 8 of x to the negative 1 over 3 multiplied by the square root, right, of u multiplied by 3 over 2 multiplied by x to the negative 1 over 3 in the denominator du, which can be simplified. As you can see, the x to the negative 1 over 3 can be simplified, and we are left with the integral from 1 to 8 of 3 over 2 multiplied by the square root of u du, which is equal to 3 over 2 multiplied by u to the 3 over 2 over 3 over 2 evaluated between 1 and 8. And going back to the original substitution, we have 3 over 2 multiplied into, because remember these boundaries 1 and 8 are valid for x, not u. So we have to go back to the original substitution, which therefore gives us x to the 2 over 3 plus 4 over 9 to the exponent of 3 over 2 divided by 3 over 2 here, and evaluated between 1 and 8. And the 3 over 2 here can cancel, so we are left with the x to the 2 over 3 plus 4 over 9 all to the exponent of 3 over 2 evaluated between 1 and 8. Which will give us, let's first substitute 8. So if we try by substituting 8 first, we'll get 8 to the 2 over 3 plus 4 over 9 to the 3 over 2 minus 1 plus 4 over 9 to the 3 over 2. Yes. Right. And if you do all the calculations from there, you should be able to get 1 over 27 multiplied into 40 to the exponent of 3 over 2 minus 13 to the exponent of 3 over 2. Right, so double check this final results there. All right, moving on to now the parametric example, which is the third one. Well, we know that for this example, we have to use the formula that tells us what? That L is equal to the integral. So let's go back to our formula. The integral So L is equal to the integral from C to D, right, of, let's write it down. So from C to D of the square root of dx over dt squared plus dy over dt squared, all multiplied by dt. So the first thing that we need to find is dx over dt here, which is just the derivative in terms of t of e to the t cos t, which will tell us that, as we can see, we have to use the product rule. And using the product rule, we get e to the t cos t minus e to the t sine t, right? And then dy over dt is equal to the derivative in terms of t of e to the t sine t, which is equal to e to the t sine t plus e to the t cos t. Right. And if we take it to the formula, what do we get? We get L is equal to the integral from, we're told that t is varying from 0 to pi over 2. So in this case, the parametric variable t is an angle. So from 0 to pi over 2, which makes sense because we're dealing with trigonometric equations. So of the square roots of, right, e to the t cos t minus e to the t sine t squared plus e to the t sine t, right, sorry, let me erase this, e to the t sine t plus e to the t cos t squared. This is all under the square root sign dt. And this will give us the integral from 0 to pi over 2 of what? Of the square root of, now we'll expand the squares. And what do we get? We get e to the, we'll first expand the first one, so e to the 2t times cos squared t minus 2 times e to the 2t times sine t cos t plus e to the 2t times sine squared of t plus e to the 2t sine squared of t, now we're doing the second one, plus 2 times e to the 2t times sine of t cos of t plus e to the 2t times cos squared of t dt. Okay, so now let's simplify where we can. So the integral from 0 to pi over 2 of what's under the square root sign. Is there anything we can simplify? Let's look. Well, we can clearly simplify the 2 times e to the 2t sine t cos t, right? Because we had these two cancel. What else? I think that is all. We can combine these two and this one and that one to get 2 multiplied by e to the 2t cos squared of t plus 2 multiplied by e to the 2t sine squared of t. we can clearly see that 2 times e to the 2t is a common factor there, so let's pull it out. The integral from 0 to pi over 2 now of the square root of 2 times e to the 2t multiplied into sine squared t plus cos squared t dt. And this is giving us the integral from 0 to pi over 2 of the square root of 2 times e to the 2t, because remember that sine squared plus cos squared is 1, right? Which means that we have the integral from 0 to pi over 2. Let's pull out the 2 there, so we have the square root of 2 multiplied by e to the t dt. And that gives us the square root of 2 multiplied by e to the t evaluated between 0 and pi of 2 over 2, which is equal to the square root of 2 multiplied by e to the pi over 2 minus e to the 0, which is just 1, so minus 1. And that should be the final answer. All right, let's move on to, if I'm correct, this is the last example. So the last example is asking us to show that the total arc length of the eclipse, right? So the eclipse that is defined by the parametric equation x is equal to 2 cos t and y is equal to sine t, and that is evaluated between 0 and 2 pi. Let's show that that is equal to that. Okay, so we are not asked to solve this question. We are just asked to show, right? Just show that it's equal to that. Okay, so let's do it. So first, we know that for these parametric equations, the formula that we're dealing with is L is equal to 0 from some A to B boundaries of dx over dt squared plus dy over dt squared dt, right? So first, let's find what's dx over dt in our case. That is just the derivative in terms of t of 2 cos t, which is equal to negative 2 sine t. And dy over dt is equal to the derivative in terms of t of sine of t, which is just equal to cos of t. So we have that. Now take it back to the formula. What we have is that L is equal to the integral. The boundaries that are given to us are 0 to 2 pi, right? Of the square root of dx over dt squared. So negative 2 sine t squared plus cos t squared multiplied by dt is equal to the integral from 0 to 2 pi of the square root of, right, 4 sine squared of t plus cos squared of t, all under the square root sign multiplied by dt outside, right? So that's what we have.